Welcome back, everyone. I hope you enjoyed our last session where we explored how artificial neurons mimic the human brain and how deep neural networks learn from data. Today, we are going to answer a very important question that comes up all the time in AI and data science. That is, what's the difference between machine learning and deep learning? And more importantly, why deep learning? Why do we even need deep learning? Last time, we talked about how deep neural networks are capable of learning complex patterns. We didn't talk much about how that compares to traditional machine learning, and that's exactly what we'll break down today. So, by the end of today's session, you will be able to explain how machine learning and deep learning differ and when to use each one. So, now let's take a closer look at how machine learning and deep learning differ in key aspects. Even though deep learning is technically a subset of machine learning, but there are some important practical differences. So now you might be wondering, if deep learning is just a type of machine learning, what really sets them apart? Well, let's break it down and look at five main differences. The first thing is how much data they need, then how features are handled, how long training takes, what kind of hardware they require, and how easy they are to interpret. So let's start with the biggest difference, that is, how much data these models need to work well. Let's say you're trying to predict the price of a used car. First, we gather a data set. Each row is one car, and columns include features like brand, mileage, model year, and condition. You might only need a few hundred or a few thousand examples, each with features like brand, mileage, model, year, and condition. Now, we choose an algorithm. The model learns patterns from the training data, like cars with more mileage tend to be cheaper, newer models sell for more, automatic cars cost slightly more than the manual ones. So, this is the step where the learning happens. The model tries to find the mathematical relationship between the input features and the car price. Now, once the training is done, now we test the model using the test data, the data it hasn't seen before. We give the car's features without the price and ask it to predict the price, and the model predicts the price. So, for small businesses or problems with limited data, machine learning is usually the better choice. And coming to deep learning, it's more advanced. It can use images of car, text like well maintained, single owner, even audio or video. It uses neural networks that learn complex patterns automatically, like this car looks more damaged in the photo, or this model is rare and valuable. So, deep learning works best when you have lots of data and want to include photos or text. So, it's like this. Machine learning is kind of picky. It wants everything in numbers, neat and clean, like a well organized Excel sheet. If you give it anything else, it's like, nope, I don't know what to do with this. So, we need to tell the model, hey, model, this is important. Focus on car age, fuel type, mileage. Deep learning, on the other hand, is super chill. You can throw it images, text, sound, whatever. It's like, cool, I'll figure it out. It learns how to pull out the important stuff from all kinds of messy and raw data. Alright, so we just talked about how deep learning loves tons of data and can handle all sorts of messy input, while traditional machine learning wants clean and structured data, mostly numbers. Now, here's where feature engineering comes in. In machine learning, since the model isn't going to do much of the figuring out on its own, we have to help it by carefully choosing and creating the right features from the data. It's like prepping ingredients before cooking. You chop, you clean, you measure everything so that the model can cook properly. Deep learning, on the other hand, it's more like a chef that says, just give me the raw ingredients, I'll do the chopping and prepping myself. So it learns the features automatically, especially with things like images or text. So let's dive into what feature engineering actually is and why it matters in machine learning, and when you still might need deep learning later, but let's now focus only on this. So this image is a great summary of one of the biggest differences between traditional machine learning and deep learning. So let's start with the top half, machine learning. You can see the car image comes in as input, but before the model can do anything, there's a person sitting at a computer. That's us, the human. We have to manually extract the features. That means deciding what parts of the image are important, maybe the shape of the car, the wheels, color, etc. Then those features go into the model for classification, and the model gives us the output, either car or not car. Now look at the bottom half, deep learning. Again, the car image comes in, but now there's no human in the middle. The deep learning model itself handles both the feature extraction and the classification. It learns what features are important on its own so that we don't have to manually tell it what to look for. So, in short, with ML, you do the feature engineering. With deep learning, the model does it for you. So that's why deep learning is so powerful, but it needs way more data and computing power to figure things out. That's one big reason why deep learning needs a lot more data, because it's learning everything from scratch, including which features matter. To summarize, in machine learning, we engineer the features. In deep learning, the model learns the features on its own. Cool, right? Now that we've covered feature engineering, let's talk about what happens next, that is, training the model. Here's the deal: machine learning models usually train pretty fast. Why? Because you already did all the hard work during the feature engineering. The model just needs to find the patterns in those clean, hand picked features. So, training might take few minutes, maybe a few hours, depending on the size of the data. Deep learning, on the other hand, takes much longer to train because they are not just learning patterns, they are also learning what the important features even are. This is a lot more work. Plus, they have way more parameters and layers to train. So it could take hours, days, or even weeks to train a deep learning model, especially on large data sets like images or videos. So, a simple way to remember this is machine learning is like solving a puzzle with hints already given. But deep learning is like solving a puzzle from scratch with no hints at all. And that's why deep learning models need more data, more time, more computing power like GPUs or TPUs to get really good results. So think of machine learning as solving a crossword puzzle where you have all the hints, whereas deep learning is like solving a zigzag puzzle where you don't get any hints, just piles of random pieces, no labels, no outlines, just raw data. So the deep learning model has to figure out what the pieces are, how they fit, what the final picture should look like, all on its own. That's why it takes longer to train. But once it gets it right, it can solve so much more complex puzzles than traditional machine learning ever could. Alright, now we have seen that deep learning takes way more time to train compared to traditional machine learning. Now let's talk about why. A big reason is the hardware they need. Machine learning is light and fast. It runs on a regular laptop or CPU. Machine learning often works with smaller tabular data sets. It doesn't need anything fancy. It works fine for smaller data sets and simpler models. Machine learning models can run efficiently on CPUs, whereas Deep learning has heavy duty needs a GPU or even a cluster of GPUs or TPUs. Deep learning is used for large scale, high dimensional data like images or audio text. Bigger data means more computational per batch. Deep learning models require GPU to handle parallel computation or large tensor operations. Next, we'll understand what interpretability is and can we interpret deep learning or not. So, what is interpretability? Interpretability means how easily we can understand why a model made a certain prediction. Like, can we explain it to a human in plain terms? Now, take a look at this image. It perfectly sums up the difference between how understandable these two approaches are. On the left, we got a calculator or flowchart that represents machine learning. Why? Because machine learning models follow clear and logical steps. It's like solving math with step by step formulas. You can see exactly how the model went from input to output. If it says no loan, you can ask why and get an answer like because the income is low and the age is above 50. So, this makes machine learning model transparent and easy to explain to others, especially important in areas like banking or healthcare. Now look at the right side. That's a brain representing deep learning. Deep learning models are like human brain. They're powerful, but we don't always know what's going on inside. They make these amazing predictions, but if you ask why it gave a certain answer, it's not so easy to explain. It's like asking your brain, why did you recognize that face? You know it's familiar, but you can't always explain how. So the key takeaway is machine learning is easier to interpret, deep learning is harder to interpret, but more often more powerful. So that's why interpretability is a big deal when deciding which model to use in real world problems. So to summarize everything what we have learned today, the first thing is the data requirements. Machine learning works well with small to medium data sets. There's no need of handcrafted features. Whereas deep learning, it needs huge data sets, learns features automatically from raw data. Then we have feature engineering. Machine learning requires manual feature engineering. You have to choose what to give the model. Whereas deep learning, it learns the features on its own, even from raw pixels or audio. Training time, machine learning trains quickly, minutes to hours, but deep learning takes longer to train, can be hours, days, or even more. Hardware requirements, machine learning runs fine on CPUs, laptops, but deep learning it requires GPUs, TPUs for efficient training. Interpretability, machine learning it's easy to understand and explain, like we don't have much complex patterns there. We have only decision trees, linear models, but in case of deep learning, it acts like a black box. It's hard to explain why it made a decision. So that's all for today. We now understand when to use machine learning and when to use deep learning, and why deep learning is often preferred for complex problems like image or speech recognition. In our next session, we'll dive deeper into how deep neural networks actually work. So, thank you. Have a nice day.